In this video, I want to show you how you can tell if a polar equation, if the graph of the polar equation is going to have any symmetry. And just to remind you, in rectangular, if you have an equation like 4x squared plus 9y squared equals 36, well, we know that's an ellipse, but even if we didn't know that, there's a way to check for symmetry. To check if a graph has y-axis symmetry, we replace x with negative x, and we see if the equation turns into the same equation. And since it does, it has symmetry. It's kind of like saying if xy is on the graph, and if minus x comma y is also on the graph, that would mean that it has symmetry because every point here would have a partner on the other side. That's how you check for y-axis symmetry in a rectangular graph. To check for x-axis symmetry, you replace y with negative y, and you see if the equation turns into the same equation as the original, or if it satisfies the equation, which it does. So that means here's x minus y, that if there's a point here, there's also a point there, and that's what makes it symmetrical. A third type of symmetry for rectangular is, am I symmetric over the origin? And you would tell that by replacing x and y with negative x and negative y. And if that turns back into the original equation, so this ellipse, as we know, has all three types of symmetry. So if there's a point here at xy, there's also a point here at minus x minus y. That's just a quick review of symmetry for rectangular. But symmetry for polar is a little bit more confusing. There are three types of symmetry in polar. Like these limisones, they have symmetry about it's kind of like the y-axis, but we call it the theta equals 90 symmetry. There are also, here's another one of these limisones, sideways this one. This one has symmetry over the x-axis, but in polar it's called the polar axis, or the theta equals 0. And a third type of symmetry we want to be able to check for, there are some curves that, like this sort of figure 8 thing. This is called polar symmetry. It's kind of like a point symmetry. If there's a point here, there's like a partner point here, sort of reflected through the pole. So those are the three types of symmetry, and I want to show you how to tell from the equation which of these symmetries the thing has. So here's the equation, r equals 2 cosine theta plus 3. And it ends up, it's a limizone, it has sort of this shape to it. And we can see that it has symmetry with respect to the polar axis, theta equals 0. If something has that kind of symmetry and there's a point here, there's also going to be a point over here. Well, if this point is r theta, this point here could be thought of as r comma negative theta. And that's why we can check for this type of symmetry by this is to check for theta equals 0 symmetry. You just replace theta with negative theta, and then simplify. Since cosine negative theta, that's an identity, cosine negative theta is equal to cosine theta. And because this equation turned back to the original, it means that r negative theta satisfies the equation anytime r theta does. Well, r theta satisfies the equation, and r negative theta also does. And that's how we check for that type of symmetry. So when there's a cosine involved, that's often when this works. R equals 2 sine theta plus 3. Well, that looks like, kind of looks like that. It has symmetry with respect to theta equals 90. And the way we check that, if this is a point, r theta, we want to check if there's also a point here. There are actually a couple of ways to describe this point, but I think for our purposes, the easiest way to describe it is going to be r comma 180 minus theta. There's another way that I'll show you, but I don't like that way as much. So if I replace this 2 sine 180 minus theta plus 3, well, good news for you. On a sine curve, if here's theta, then here is 180 minus theta. Let's say this little red piece is theta, so that's 180 minus theta. So those are equal to each other. And you can always replace 180 minus theta, sine of 180 minus theta, with sine theta. There is another way, and by the way, these tests sometimes don't. If the test says it's got symmetry, then it definitely does, but if the test says it doesn't have symmetry, there's a chance that it still has symmetry. It's just that it's a little confusing to explain why some points have multiple names, and it's a little confusing. But definitely, if it passes the test, it has the symmetry. The other way of naming this point, which would at least seem to be a good idea, would be to call it negative r, negative theta. I just want to show you that. So here's negative theta here, and if I'm pointing in that direction, but then I go negative r, I get to that same spot. So in theory, if I replace r with negative r and theta with negative theta, it's a way of checking. But look what happens. Even getting to use the fact that sine negative theta is negative sine theta, it didn't seem to work. Even if I divide everything by negative 1, I get 2 sine theta minus 3, which is not the same as this. So you might say, well, it doesn't have that symmetry. These tests actually, while they can verify that it does have the kind of symmetry if the test works, if it doesn't work, we could just say not conclusive. We're not sure. We can't actually say, based on a test not working, that it doesn't have symmetry, because sometimes points are named different things and it still has that symmetry, but it doesn't realize it based on the test. So I'll say no conclusion based on this, the fact that this equation did not turn back into this. But the way we did it before, we got definitive conclusion. Now here's a type of equation we haven't ever seen before, r squared equals 16 sine 2 theta. It turns out it has what's called polar symmetry. And I'll show you how you could have known that. If this is r theta, its partner point here is r comma theta plus 180. Right? If you rotate this 180 degrees, it ends up over here. And if that happens for every point, you're going to have this kind of symmetry about the origin. So I'm going to do the check. R stays as an r. 2 times theta plus 180 becomes r squared equals 16 sine 2 theta plus 360. But then you can just get rid of the 360, because sine of 2 theta plus 360 is the same angle as 2 theta. So this did work, and it did have that type of symmetry. So to summarize, our checks are for theta equals 90, I like to replace theta with 180 minus theta. For theta equals 0, I like to replace theta with negative theta. And for polar, I like to replace theta with theta plus 180. Again, if any of these tests fail, we can't make a conclusion at that point one way or the other, but if it passes, it definitely has that type of symmetry. Why don't I also make a note here for the theta equals 90. I'll just mention it, or r goes to negative r and theta goes to negative theta. That would work also, but again, if it works. If it doesn't, there's still no conclusion. As an example, here's something, r equals 4 cosine 6 theta. If I test the different types of symmetry, like theta equals 0, for theta equals 0, I replace theta with negative theta, which turns into negative 6 theta, but cosine of negative 6 theta is the same thing as 4 cosine 6 theta, so it works, so it does have that type of symmetry. If I try theta equals 90, and I say r equals 4 cosine 6 times 180 minus theta, if I distribute through, I get 4 cosine 1080 minus 6 theta. 1080 is a multiple of 360, so I can just kind of get rid of it. And cosine of negative 6 theta is the same thing as cosine 6 theta. So whatever this thing looks like, it has that symmetry. It has the theta equals 90. And for polar, r equals 4 cosine 6 theta plus 180. That eventually turns into 4 cosine of 6 theta plus 1080. But since 1080 is a multiple of 360, I can get rid of it. So whatever this thing is, it has all three types of symmetry. On the other hand, 4 cosine of 7 theta, that one, if I try for theta equals 0, that will work, because r equals 4 cosine of negative 7 theta is the same thing as 4 cosine of 7 theta. But if I try theta equals 90, it actually doesn't work. 7 180 minus theta. And the reason that's not going to work is 7 times 180 is not going to be a multiple of 360. It's going to be 1260 minus 7 theta. But I'm not able to just cross that thing out like I could before. Okay, so those are the different symmetries. Maybe I should mention also, we use the fact that sine negative theta equals negative sine theta. We use the fact that cosine of negative theta is equal to cosine theta. We use the fact that sine of 180 minus theta is equal to sine theta. But in case we ever need it, cosine of 180 minus theta, here's a cosine curve. So here's, if that's theta, 180 minus theta is down here, is equal to negative cosine theta. So these things are not, it's not equal to cosine theta. Maybe that will come in handy. So that is the way to check for the three types of symmetry in polar graphs. I'm going to repeat again. If it passes, if one of these tests passes, it definitely has the symmetry. But if one of the tests fails, it actually still might have that type of symmetry. So we'll either say yes or not conclusive.